Hi, my name is Andy Trent,
And I'm Nicholas Nates.
and our project was a translational rack and pinion system. For the hardware on the electrical side, we had a 12-volt DC motor with an Adafruit H-bridge driver, an 80-foot voltage current and power sensor, a 12-volt power supply, and an Arduino Nano. And on the mechanical side, we had a rack and pinion that we built, and also a mounting structure that we built as well.
For the electrical side of the electromechanical system with the rack and pinion, we had a Nano Arduino 33 IoT that was connected to an H bridge so that the motor could function correctly. And that H bridge was connected to a power sensor that could measure the amperage and the power of the whole system. Code-wise, we coded the rack and pinion or we coded the DC motor to rotate the gear to translate rotational motion into linear motion, and we did this with bidirectional motor control. Furthermore, we had the power sensor coded so that it would, with every revolution, it would check for RPM, power, amperage, and voltage. And we had to do it X amount of times in each direction. For the motor to work correctly, we also built a motor mount and an axle adapter so that it could rotate the gear in an efficient manner.
And also stay attached to the gear shaft whenever it's spun. And so for the simulation, we had um, we had to simulate a rotational motion using the ideal rotational motion sensor, and that would translate into the real life gear that we were spinning. And so to simulate the translational motion, we would calculate uh, the rack speed, the rack acceleration, and the rack position using multiply blocks that would calculate for us. The data given from the simulation was RPM and voltage, and then what we solved for was the current, the power, the time, and the motion of rigid body parts. And then for the experiment, uh, we collected the RPM, the voltage, the current, the power, and the time from the ENA 260 power sensor. Our results for the voltage and the RPM were consistent with the simulated. However, there were some outliers due to either friction or the construction of our rack and pinion system, which caused some friction as well. And our current, um, it did not follow the theoretical, the Simulink simulation, as the sensor was most likely not working well. And that'll be all.